Hi everyone, in this video lecture I'm going to talk about how we use mineral properties to identify different types of minerals and also how we categorize them or classify them by putting them into groups based on their chemistries. When we talk about mineral properties, we're talking about the physical properties that minerals display. Those physical properties include things like color, specific gravity or density, streak, habit, cleavage or fracture, and a number of other types of properties. These are used primarily to identify minerals. So as geologists, we're very interested in discovering what minerals are contained in what rocks because we can learn a lot about the rock type and how it formed and what geologic process would have been active in that part of the earth to produce those minerals and those rocks. Mineral physical properties are very closely tied to both the crystal structure, so how the atoms are joined together, what kind of bonds they form, and the chemical composition of the mineral. So a mineral like halite, which contains ionically bonded sodium and chlorine arranged in a cubic structure, will have very different properties than, say, a diamond, which is made of covalently bonded carbon atoms. I'm using those two examples since they were discussed in the previous video on minerals. Some of these properties are very diagnostic and others are not. I'm including an example here of the mineral pyrite. If you looked at this mineral, either in person or in the picture here, you could ask yourself, how would I describe the physical properties of this mineral? And some of the things that you would probably say is that it's cubic. So hopefully you can see that the pyrite is forming these cubic forms. So I'm just kind of tracing one right here in blue for you. So they're growing together, but these are a number of different cubic crystals of pyrite. But it's cubic, but it doesn't look anything like halite, right? Because it has a very brassy color. Its luster is metallic, so it has a sheen to it that makes it look like the crystal faces are pieces of metal. It has a high specific gravity, so it would feel very heavy if you were to hold it in your hand. It has striated faces, so striated faces, I'm referring to these lines here, those are called striae. It has a black streak. We'll discuss what a streak is in a moment. And it smells of sulfur. So that's a unique property, very diagnostic of pyrite, because of course pyrite has sulfur in its mineral formula. Let's discuss color first. Color is simply the way that a mineral interacts with light. For some minerals, color is diagnostic. For example, something like malachite down here. Malachite is always green, has that very distinctive kind of swirly green color. Kyanite, we saw that in the last video I made on minerals, is always blue. However, some minerals may exhibit a really broad color range, and quartz, one of the world's most common minerals, is an excellent example of that. Quartz can be clear, it can be milky white, it can be pink, purple, gray, yellow, it can be a dark red. It can take on just about every color and every hue you can imagine. Very often these color varieties reflect trace impurities, so trace amounts of elements that are not seen in the mineral formula itself. Streak, what is streak? Okay, this is kind of an unusual mineral property by which a mineral leaves a colored powder behind when the mineral is rubbed against a plate. So some minerals, particularly those that have metallic lusters, so the way they reflect light off their surfaces gives it a metallic sheen. For minerals like that, if you were to scratch it against a white tile, like what is shown in these pictures, it would actually leave behind a colored powder. And we would call that colored powder the streak. And in this example, we've got two metallic minerals. We've got cinnabar over here and pyrite over here. And when we streak them, you can see that cinnabar leaves a very distinctive reddish-brown streak, whereas pyrite leaves a black one. So this is one way that you might be able to identify cinnabar. Now, most minerals that do not have metallic luster will not leave a streak of any color. So this is only a mineral property that is useful for some very heavy or dense metallically lustered minerals. Okay, I probably should have introduced luster first, since I just discussed it at length with respect to streaking metallic minerals. Again, luster is the way that the surface of a mineral scatters light. So when light reflects off of very dense minerals, most of it tends to be reflected, and that will produce this metallic sheen like you saw in the pyrite. For a lot of other particularly less dense minerals, light will not be scattered. Some of it will actually pass through the mineral itself, making the mineral look translucent like the diamond. Some of it will be refracted, some of it will be reflected off the surface, and the combination of the way that the light gets scattered around the mineral will produce these different sheens that the mineral has on its surfaces. So for example, we would call gypsum, which is this mineral down here, we would call this satiny or maybe silky. So you can see the way that it's reflecting light makes it almost look like satin fabric of some kind. Serpentine, which by the way is the state mineral of California, is said to have a greasy luster. And so hopefully you can see when you look at this picture here, particularly in that green spot, it almost looks like if you were to wipe your thumb across the surface of that mineral, it would come away with like a grease or an oily feeling on your thumb. It doesn't, by the way, that's just the way the mineral scatters light. And then there are some that just look kind of opaque, and that don't look shiny or don't have a real distinctive luster, and we would call those dull. But over here we've got kind of the full range of lusters that we might give to a mineral that is non-metallic. Hardness. Hardness is the resistance of a mineral to scattering. If you saw the other lecture that I posted on minerals, then you'll remember that the hardest mineral out there in the world is diamond. So it is a 10 on the Mohs hardness scale. But I want you to notice that the Mohs hardness scale is actually logarithmic. And so the next hardest mineral, corundum, is actually an order of magnitude smaller. The weakest mineral down here is talc. Talc is what makes up talcum powder or baby powder. So it is so weak that it can be turned into powder with, just a squeeze of your hand. Another example of a mineral that is very, very weak that you might remember from our last lecture is the polymorph of diamond called graphite. So for those of you that may be taking notes on this lecture using a pencil, that's probably like 0.1% of you, you are actually leaving little streaks of graphite on your paper. So pencil lead is no longer made out of lead, it is made out of the mineral graphite. And little pieces of graphite are flaking off of your pencil and being deposited on the paper, and that's how you can see what you're writing on your page. Specific gravity. You can think of specific gravity as being synonymous with density. It's actually not. Specific gravity is technically the weight of a volume of a mineral compared to the weight of an equal volume of water. But for now, let's just consider it to be the same as density. So something like galena, that's this mineral over here, will feel very dense because half of what's in that mineral are atoms of the element lead, and lead is a very, very heavy element, lots of protons and neutrons in its nucleus. An equal sized chunk of quartz, which is what's shown over here, will feel considerably lighter because quartz is only made of the elements silicon and oxygen, which are much, much smaller atoms than lead. So very very light or low density elements making up quartz. Quartz is also mostly covalently bonded, which means that there's a lot more separation between the elements themselves, making for a less dense structure. Crystal habit. Habit refers to the shape of a crystal when it's able to form well-formed faces. So you may recall from our last lecture the term euhedral. So euhedral just means well-formed. So having perfect crystal faces, I believe, is how I described it before. So a euhedral crystal is one that's had the time and the space and the opportunity and the chemical availability to grow into its idealized macroscopic version of its internal atomic arrangement. And so that is actually very distinctive of the crystal structure of a mineral. So, you know, the cubic structure or the rhombohedral structure or the dodecahedral structure of something like garnet. Garnet will always form these 12-sided kind of soccer ball-like forms if allowed to become euhedral. These habits are very diagnostic. They can tell us a lot about the mineral that you're looking at if you can identify these forms. Here are some examples of very different crystal habits. So on the left, we've got our favorite kyanite crystal. Okay, kyanite is actually a pretty rare mineral, but it shows up a lot in these lecture slides because it's, well, pretty. It has that diagnostic blue color, and also because it forms a crystal habit that is also very recognizable, and we call that a bladed crystal habit. It has almost the shape of a knife blade. On the right, we're looking at an asbestos mineral, and an asbestos mineral is said to have a fibrous habit for obvious reasons. The mineral asbestos, which is actually a class of minerals, tends to form these fiber-like crystals, and that's what makes them so dangerous. They can be inhaled into your lungs, and they can really badly damage your lungs and your entire respiratory tract. Okay, fracture and cleavage. These refer to how a mineral breaks. If a mineral breaks to form distinctive planar surfaces that have very specific orientations, then that mineral is said to have cleavage, and each surface then becomes a cleavage plane. So if a mineral develops cleavages, what that means is that it has defined planes within its crystal structure that have weaker bonds between the atoms. If a mineral has equal strength bonds in all directions, then it won't cleave. It will simply fracture, and I'll show you a picture of that in a moment. Here are some examples of different kinds of cleavage that can form in minerals. Something like halite, we keep returning to this one because it's a great simple example. If you were to take a hammer or a knife and cut up a piece of halite, it would cleave into perfect little cubes. And that's because it's equally weak in all directions. Those ionic bonds are fairly weak. So if you were to try to break a big crystal of halite, it will just break into smaller and smaller cubes. A calcite crystal will just break into smaller and smaller rhombs. Hopefully in this calcite crystal you can see that it makes a perfectly rhombohedral form where none of the angles are 90 degrees. Okay, and like I said, some minerals that have equally strong or weak bonds in all directions won't cleave. Instead, they will fracture. And that fracture can be either highly irregular, so sometimes we call that hackly or jagged or irregular fracture, or it can form this very distinctive clamshell-like pattern when it fractures. We call that conchoidal. If you've ever broken a piece of glass, then you've seen this conchoidal fracture develop, and so that clamshell pattern I'm referring to is here. And that's very diagnostic of the mineral quartz. It will always form this conchoidal fracture when broken. Sometimes it can be very difficult for students that are just starting out in geology to recognize the difference between a crystal face and cleavage planes. And adding to that complexity is the fact that cleavage planes do sometimes form in orientations parallel to crystal faces. But on the right, we've got quartz here, and you can see these beautiful prismatic crystals that it's forming. So prismatic would be a description of crystal habit, so very diagnostic of quartz. And all of these here, like this is a crystal face and this is a crystal face. These are not cleavage planes. These are not planes of weakness along which the mineral will break if it's subjected to force. These are the exterior surfaces of beautifully formed euhedral crystals of quartz. Remember, quartz in fact doesn't cleave at all. If you were to break this prism of quartz apart, it would just have conchoidal fracture. On the left, we're seeing perfect 3 planes of cleavage in the mineral fluorite. And so cleavage will produce these repeated planes. So like here's one plane, here's another plane, here's another plane, and you can see these stair steps are repeating themselves. If you are taking the Geology 102 lab, hopefully this is something that you'll actually have some practice identifying and looking at with real samples at some point. Other special properties that some minerals can have include magnetism. So not surprisingly, the mineral magnetite is magnetic and will attract obviously magnets and other metal things like these nails here. Calcite is unusual because it will react with acid based on this equation here. If you put some dilute HCl onto calcite, it will effervesce and release CO2 gas. And so, believe it or not, geologists actually do sometimes walk around in the field with little dropper bottles of dilute acid, because sometimes calcite, if it doesn't form these beautiful rhombohedral, euhedral crystals, can be difficult to identify. Okay, lastly, I want to touch on mineral classification. So we've got all these different types of minerals. We know something now about how they're defined, how they form, how we might go about identifying them. But how do we group them? So, how do we figure out a way of putting minerals into different classes and putting the ones that are alike together and those that are not alike together, etc. In geology, we typically classify all minerals based on their principal anion. Remember that anion is the negatively charged ion form of an element. Or we use their anionic group. So that would be a molecule that includes one of these negatively charged ionic species. Far and away, the most abundant mineral class on planet Earth are called silicate minerals. And every silicate mineral ends, so the mineral formula will end in SiO, because it has as its fundamental building block this anionic group that creates the mineral structure. Other minerals might end in just O for oxygen. Those would be called oxides, or S for sulfur. Those would be called sulfides. If sulfur is bonded together with oxygen to make an anionic molecule, then we would call that mineral that contains that molecule a sulfate. Carbonates would contain this anionic complex or molecule as part of their formula. So you can look at some of the examples that are shown in the rightmost column here. So calcite is a perfect example of a carbonate. It ends in that CO anionic complex. Notice also, however, that mineral formula have to be charge neutral. So while all carbonates contain this anionic complex, the 2- that is shown here is balanced by the calcium, which is a cation, such that the resulting mineral formula is charge neutral. Maybe you were wondering, why is it that silicate minerals are the most abundant minerals on Earth? Well, the answer to that is easy. That's because oxygen and silicon make up over 75% of all the elements in the Earth's crust. Okay, so therefore, these two elements, when they join together, and they're very reactive. So if you put silicon and oxygen together, they will very quickly match up to form the SiO4 4- anionic molecule. And then that molecule can go around and it can bond with potassium, magnesium, sodium, calcium, iron, aluminum, or a combination of those. These all form positively charged cations that will balance out this negatively charged anionic complex, and the result will be a silicate mineral. So silicate minerals, including the mineral quartz, are far and away the most abundant mineral class in the Earth's crust. And again, that's because Si and O are the most abundant elements in the crust. So for that reason, we tend to pay a lot of attention to silicate minerals. Silicate minerals are the most abundant, and there's many different types of them, and they are big players in most rocks of planet Earth. Almost 100% of the mantle, for example, is made of silicate minerals. So silicates, I've told you what the formula is. Silicates have 4 oxygens bonded to every 1 silica cation, and they form these little pyramid shapes that have a 3-sided bottom. So each one of these red balls is an oxygen atom, and so you can see that 3 of them form the stable base of the silicon tetrahedron. That's what we call this form. And then you've got to nestle your little positively charged silicon cation in there, and then stick another oxygen on top, and what you end up creating is a form that looks like that looks like a little pyramid. And those pyramids, the silica tetrahedra, form the building blocks of all silicate minerals. I'm going to leave this lecture with a couple of questions for you. These are multiple choice questions that we will discuss together as a group when we chat for our live Zoom meeting on Thursday. So be thinking about these. What is the correct answer here with respect to silicates? So you might want to pause it and read your options here. And then one last question for you. When you scrape a mineral along a ceramic plate and observe the color of its powder, what physical property are you checking? So maybe have a pause here and think about this one too. All right, I will see you later.